This video covers the nomenclature of inorganic compounds from page 7 to page 12 of your General Chemistry 1 Laboratory Manual at Xavier University of Louisiana. The periodic table in your lab manual is on page 187. This is the periodic table that you will be allowed for use during your quiz and exams.
Okay, so we're starting Nomenclature of Inorganic Compounds on page 7 of the lab manual. So the first thing is your periodic table doesn't have it, but you should be aware of there's this line that's typically drawn. Sometimes they're color-coded, sometimes it's a line like this. There's a line on the periodic table among the elements here. This stair step here, it actually goes below hydrogen also. So all of these compounds from boron to neon and down to these in the corner. So this entire corner here, these are called nonmetals. Hydrogen is also a nonmetal, and everything else on the periodic table is a metal. So the vast majority of elements are metals. It's only these in this corner above the stair step, above and to the right of the stair step. These and hydrogen are the only nonmetals. Everything else is considered to be metals. Okay. Now, so the next thing on here, so obviously these are elements, and you already kind of know that before. So some of the obvious things, iron, cobalt, nickel, you would imagine those are metals. Nitrogen, oxygen, fluorine, you should kind of recognize those as nonmetals, right? So it kind of makes sense. So these are all metals. These up in the corner here are all nonmetals. Now, the main difference between metals and nonmetals is when it comes to ions. So first of all, any of these can exist as a neutral atom. So for instance, hydrogen will have, its atomic number is 1, it'll have 1 proton and 1 electron. So 1 positive, 1 negative, they add up to be 0. So an H atom is 0 charge on it. Same thing for lithium. Lithium has 3 protons, 3 electrons. So the overall charge on it is 0 because there's 3 positives, 3 negatives, and they cancel each other out. Okay. Now, we can have, in addition to having a neutral compound with equal number of protons and electrons, we can also have ions. Ions means there's a different number of protons and electrons. So there's an overall charge. So for lithium, for instance, if we take away, if we take away one of the electrons, now we have 3 protons and we only have 2 electrons. So that means that lithium is going to have overall a +1 charge. So for beryllium, it turns out that you would lose 2 electrons. We'll talk about that in just a minute. So it would have a +2 charge. So all of the metals always form positive charges. They essentially, in nature, cannot form a negative charge. They can only form positive charge. Hydrogen also forms a positive charge. The reason why it's written over here on the first column is because, like all the elements on the first column, like all the metals on the first column, it also forms a +1 charge. So hydrogen can be either 0 or +1, nothing else. And the same thing for lithium, sodium, potassium. So the metals and hydrogen all form positive charges based on their position, which we'll talk about in just a minute. The nonmetals all form negative charges. Okay. All right. So an ion just means that there's a different number of protons and electrons. Essentially, ion means that there's a charge on it. There's an overall charge. So again, if you have an equal number of protons and electrons, there's no charge. In that case, you have an atom. If there's unequal number of protons and electrons, then you have an ion, and you have an overall charge on it. If it's a metal, it'll have an overall positive charge. If it's a non-metal, it'll have overall negative charge. Okay, so for the metals, now it turns out, and you'll learn much more about this later in lecture, but you're just responsible for being aware of this to start with, is it turns out that all of the metals in the group 1, their ion is only +1. So that means that lithium can be either lithium 0 meaning 3 protons and 3 electrons, or it can be lithium plus 1. So that would be 3 protons and 2 electrons. That's it. You can't do anything else with it, or not in nature. It doesn't exist in nature as anything besides either pure lithium 0 or lithium plus 1. That's the only two choices in nature. We can create others in the laboratory, but for nature, what naturally occurring, it's either 0 or plus 1. For all of the metals in group 2A, this column right here, the rare earth metals, I think, these all form plus 2 charges. So beryllium can be either beryllium 0, 4 protons, 4 electrons, or it can be beryllium plus 2, 4 protons, 2 electrons. It can't be anything else. It can be plus 1, it can be plus 3, it can be anything else. It can either be 0 or plus 2. Now, in group 3, now boron is a non-metal, so that's different. But aluminum is the first metal in group 3A, and that one will form a plus 3. So you notice the trend here? In group 1, the metals form plus 1. In group 2, the metals form plus 2. In group 3, the metals form plus 3. Now, aluminum is the only one that is in group 3 that forms a plus 3. The others are different, and that's what we're about to talk about now. All right, so for all the metals, again, hydrogen is not a metal. All the metals in group 1 form plus 1s, always. Group 2s always form plus 2s. Group 3, which is only aluminum, forms plus 3. Everything else, all the other metals, the transition metals and the post-transition metals, can all form different charges. So, for instance, you've probably heard a little bit about iron. So you know that iron is in vitamins, right? The iron, and you've probably hopefully been told that the iron in vitamins is not the same as the iron on rust. So the iron in vitamins, what was essential for your body is iron 2, Fe2+. What's on rust is iron 3, so Fe3+. And so there are different charges on them. Now, magnesium can only be plus 2. It can't be anything else. So we know that it's plus 2. But with iron, it can be either plus 2 or plus 3. So what's the easiest way to differentiate between Fe2+ and Fe3+? Well, just to use a number. And so what we'll do, just to make it clear, is we'll use a Roman numeral. So Fe2+ is iron 2 ion. Iron 3, or Fe3+ is iron 3 ion. Okay? All right, let's switch over to the whiteboard. Okay, so now for group 1s, group 2s, and for aluminum, and this is on a handout that I've provided to you that's available on Brightspace in the content section. So you already have this. So again, just a reminder, so if we have for sodium, we can either have Na or we can have Na+. Na2+ does not exist in nature. So it's either Na0 or Na+. So this would be, lost my periodic table now. Anyway, equal number of protons and electrons. This one has one less electron. So this one would be called sodium. This one is sodium ion. Because if we know if it's an ion, that it has to be plus 1, because that's all it can be. With magnesium, this is magnesium atom. This is magnesium ion. So one small difference in the name, but a huge difference as far as chemical properties and everything like that. So magnesium is extremely different than magnesium ion. But that's all we need to designate, because we know if it's magnesium ion, it has to be positive because it's a metal, and it has to be plus 2 because it's group 2. So all we need to do is just to say sodium ion or magnesium ion, and we know that it is. This compound right here is not called sodium. It is sodium ion. The other one is sodium, and there's a huge difference between these two compounds. So if you write this, call this sodium, it is wrong. Wrong, wrong, wrong. That is sodium ion. Okay, now, again, what we run into is we have Unlike sodium and magnesium, iron can have two very common, I think it can actually have a few more, but these are the two most common. These are very, very common in nature. And so this one, we would just call this one iron 2 ion. Again, we do need the name ion, has to be in the name. And this one we're going to call iron 3 ion. Now, this is usually the biggest problem that we run into in naming is the Roman numeral. The only thing you need to remember is that if it's group 1, group 2, or aluminum, it doesn't have a Roman numeral. Everything else does. The vast majority of metals will have a Roman numeral to them. So always keep that in mind. So the only ones that don't have a Roman numeral are the group 1s, the group 2s, and aluminum. That's it. Everything else has a Roman numeral to it. So most of these will have Roman numerals. So that includes not only the transition metals, but also the post-transition metals, everything except for aluminum. So group 1s, group 2s, and aluminum are the only ones that don't have a Roman numeral. Everything else does have a Roman numeral, okay? All right, now there's one tricky one. Hg is mercury. Hopefully you can kind of quickly recognize that this one would be mercury 2, right? Oops. Sorry, my handwriting's not too good. It turns out that there is no, that doesn't exist. What happens is when you form that, it's diatomic, like so. So that means essentially you have one here connected to another one, and then overall there's a 2+ charge on it, which means that each one has a +1. So this one is called, and this is the one that gives students the absolute biggest trouble, and it will give you the biggest trouble also. So just be aware of it. It'll give you trouble. But mercury 1 is Hg2 2+. So there is no Hg+, it doesn't exist. If mercury forms a +1 charge, then two of those atoms come together to form a diatomic. So, all right, so just so you're aware. Okay, that's the one that's going to give you the biggest trouble. All right, now, you probably haven't seen it yet, but we're going to expect you to know polyatomic ions, which are composed of more than one element. They form together in certain ions, so they all have charges to them. All of the polyatomic ions you're responsible for are all negatively charged except for one, and that's ammonium ion. And that one will basically act as if it's a metal, so you need to be aware of that. We're going to cover the anions in just a minute, but now while we're talking about metals, is a good time to actually talk about nitrogen, 4 hydrogens, and has a +1 charge. This is called ammonium ion. There's no Roman numeral to it, and it always has a +1 charge on it. Now, that's not to be confused with, later we'll talk about ammonia. Notice no ion. These are very different. They're very different. So, but ammonium ion, it is considered to be a metal. So if you see ammonium in a compound, it typically means it's an ionic compound, which we're going to talk about in just a minute. So ammonium ion is considered to be an honorary metal ion. All right, okay. So now for the nonmetals. Now for the nonmetals, I said form a negative charge. So looking for Now, I always have students on their periodic table always write this on there, but it's not really necessary. So if we look at the periodic table, the nonmetals, then it's going to be boron, carbon, nitrogen, oxygen, fluorine, and neon here. This is group 3. This is group 4. This is group 5. This is group 6. Wait a minute, that's not right. Here, wait, let me start over and write it a little bit farther apart. Boron, carbon, nitrogen, oxygen, fluorine, neon. Okay, so this one is 3. This one's 4. This one's 5. This one's 6. This one's 7. And this one's 8. Now, it turns out that boron can be either 0 or it can be -5. Carbon can be either 0 or it can be -4. Nitrogen can be either 0 or it can be -3. Oxygen can be either 0 or it can be -2. Fluorine can be 0 or -1. And neon can only be 0. So where we get this from is the group number minus 8 equals the charge. Okay, so nitrogen is group 5. 5 minus 8 is -3. Oxygen is group 6. 6 minus 8 is -2. Fluorine is group 7. 7 minus 8 is -1. Neon is group 8. 8 minus 8 is 0. In other words, you can't form an ion. So it's the group number minus 8 will give you the charge for a nonmetal, and it'll always be negative. Okay. All right. Now the other thing is, so now also when we write the charges, especially for negatives, we write the number and then the sign. So instead of -4, which could be a -4 exponent, we'll write 4 minus just to designate it from being an exponent. So that's the purpose. That's the reason why it's written backwards, basically. So this one is carbon. So it's a carbon atom. This one, what we're going to do is we're going to take the root of the word and then we're going to add IDE ion. So typically anything that's negatively charged will end in IDE. So carbon atom versus carbide ion, oxide, fluoride, nitride, boride, anything like that, sulfide. So if it's negatively charged, it typically will end in IDE. So a negatively charged ion will typically end in IDE. Okay. All right. So looking at the exercises on here. So the first one that they give you in exercise 1 is chloride ion. So chloride would refer to chlorine. So the root for chloride would be chlorine. So it refers to chlorine. It says ion, so we know it's negatively charged, and it's an ion, so it's negatively charged. And so we look, and chlorine is in group 7, so 7 minus 8 would equal -1. So put a negative sign there. We don't need to put the 1, just a negative sign is fine. So that would be chloride ion. All right, what about the next one down would be nitride ion. So nitride is going to refer to nitrogen. Again, IDE. It's going to be its non-metal negatively charged. So nitrogen is in group 5. 5 minus 8 is going to give us, -3. And so we're going to write that as 3 minus. So again, the number and then the sign afterwards. Same thing if you're doing positives. If it was 2 plus, You know, if it's positive 2, you put 2 plus, not plus 2. So that would be nitrite ion. Okay, now going from, and so you're going to be responsible for being able to go from name to formula or formula to name for any of the ions and any of the compounds that we're going to cover. So next compound we have, next ion we have listed on here is S2 minus. So first of all, S is going to refer to sulfur. Oops. And then we know we're going to take the end of it and change it to IDE. And add ions, it's an ion. So this would be sulfide ion. Okay. The other one we have on here is I minus. So the element is going to be iodine. And so we're going to take this last part and we'll change that to iodide ion. So, okay, all right, so that covers the elements. So again, metals will be positively charged, non-metals will be negatively charged. But just like when I kind of alluded to with ammonium, is there are what we call polyatomic ions, which means it's composed of more than one element, and they form sort of like a molecule, but they're charged, which means that they're ions. So we call those polyatomic ions. Again, it's sort of like a molecule. If you're familiar with like carbon dioxide or something like that. This is sort of like that, multiple elements, but it's in a specific pattern, specific numbers, and it has an overall charge to it. So you'll learn more about those once you get later in GChem 1 lecture. But for now, we just want you to know what these are. So the first ones we start with are, there's 4 basic oxyions that you're responsible for. So that would be ClO3 minus, which is chlorate ion. There's PO4 3 minus, phosphate. Ion. And nitrate. And then sulfate. Okay, so these are 4 ions that we expect you to just memorize, basically. You have to know these. Now, we're going to derive a lot more based on these from these base structures, but these are the base structures. So you just basically have to memorize them, the name, the formula, and the charge on them. Notice that phosphate has a 3 minus and chlorate has a single minus charge on it. Okay. Once you know these, then we can make a bunch more derivatives. Now, the polyatomic ion sheet that they typically give you in lecture to memorize, it'll have a bunch of ones listed separately without any connection. In this, we show you how the connection works. And so it should make things relatively easier in that by memorizing these 4, you'll actually, and a couple of really simple rules, you'll learn like 10 different ions. So it's a way of shortening things and showing you the connection between things. So these all have basically derivatives associated with them. So the way the derivatives are going to work, now what you may want to do is on page 9, if you have your lab book, is dog ear that page because you'll probably refer back to this. So we're going to use chlorate as a sample, but realize that all of these are going to work the same way. Okay, so we're going to start out with our chlorate that we just learned, the one that we've memorized. So we memorized that ClO minus is called chlorate. Ion. Okay, so that's our base. That's what we're starting with. Now, it turns out that there's a related one. Oops. Looks exactly the same, except for there's just one less oxygen. So that's the only difference. Same charge, same chlorine, everything's exactly the same except for there's one less oxygen. If there's one less oxygen, then what we do is, and there's only a couple of changes that we make, a couple of simple rules, is if there's one less oxygen, then we're going to change the ATE, oops, you change it. Change the ATE to ITE. So there's basically only two suffixes. There's ate and there's ite. That's actually the only two suffixes we use. So that makes things relatively easy. All right. So ite means one less oxygen than the base structure. Simple enough. So that works for all of the four that we did. There's, in addition to a phosphate, there's a phosphite. In addition to nitrate, there's a nitrite. In addition to sulfate, there's a sulfite. So for all of those ones that we just learned, works exactly the same way. Now it turns out that chlorate is kind of special, is that there's also a couple extra ones too. So there's also one that has one more oxygen than the base form did. So now we only have two suffixes. Yeah, we only have two suffixes, ate or ite. So we don't have any other ones. And this is relatively rare for most of our compounds anyway. So what we're going to do is we're going to use a prefix. So the prefix for one more or above is per. So per means above. So it's still ate, but this time we've added per onto it. And again, per means above, because we only have ate or ite. That's only two choices we have. So if it's one more than the ate, than the highest form, then we have to add a prefix, which is per, which means above. All right, now it turns out for this one, we also have one more form, which is, again, very unusual. So this one has one less oxygen than the ite form does. Again, we only have two suffixes, so we need a prefix for this one. So the prefix for below, in other words, one less oxygen, below is hypo. That's where you get hypodermic from. Hypo, and again, notice that this is chlorite because there are only two suffixes. And so it's still ite, but this time we've added the prefix hypo to it, like so. Okay? Now, the other thing to be aware of this is that for this one, we told you that there's that the chlorate, the sulfate, the nitrate, and the phosphate all work exactly the same way. Primarily, they have these two forms here. Very few of them have the per or the hypo, but they have these two forms. But also, in addition, what they don't really tell you is that we also have bromine and iodine also do the same thing here. So bromate would be BrO3 minus, iodate would be IO3 minus, and then all of these derivatives would also be the same for bromine and iodine. So typically compounds that are in the same family, in other words, the same column on the periodic table, will behave the same way. So they do expect you to be able to recognize perbromate or hypoiodite and so forth like that. So in addition to the chlorate, they also expect you to know the family for bromate and for iodate. So just kind of be aware of that. Okay. All right. Now, looking on down. So again, this is a useful page for you to reference, page 9, where they do cover the names of the families from this, because this is very, very useful. So in exercise 2, so they say sulfate is SO4 2 minus. They want to know what the formula for sulfite is. Now, sulfate is SO4 2 minus. Sulfite, what we learned was that the difference between ate and ite is that ite has one less oxygen. So the sulfite ion should be exactly the same as sulfate, except for just one less oxygen. Same charge, same everything, just one less oxygen. So the sulfite ion is going to be SO3 2 minus. So again, the charge is the same. Okay. Now, the next one down, they say nitrite ion. If nitrite ion is NO2 minus, what would NO3 minus be called? So NO3 minus, the difference between NO2 minus and NO3 minus is that NO3 minus has one more oxygen. Now, NO2 minus is nitrite. So we're going from nitrite and adding one more oxygen, which means that we can change the suffix on this. So we change it from nitrite to nitrate. So NO3 minus would be nitrate ion. Okay, if iodate ion, so again, iodate, like chlorate, but it's in the same family. Iodate ion is IO3 minus, then what would hypoiodite ion be? Okay, so first of all, we're changing the suffix from ate to ite. So that means that we're losing an oxygen. And then we're adding the hypo on there, which means we're losing one more oxygen. So we're going to lose two oxygens out of this. So the hypodite ion would be IO3 minus minus two oxygens, which would be IO minus, much like the hypochlorite that you see on the page there. Okay, now, the next one down, number 4, down bottom page 9, there's 9 polyatomic ions listed on here. The reason why they're listed here is because there are no other derivatives, so you don't have to worry about the eights and ites and hypos and pers and everything like that. Basically, these are just complete standalones. So you're responsible for memorizing these 9 polyatomic ions and names, formulas, and charges. Okay, now, the next thing down here is hydrogen-containing ions. So now usually what I do is on this one, I'll use this example. So this is phosphate ion. Oops. Like so. Okay, now what we can do is we can add H pluses to this and still be an ion. Now if we add an H plus and a PO4 3 minus, plus 1 and minus 3, it's going to give us an overall charge of -2. So we have changed it. Now the only difference between this and this is that we've added an H plus to it. So all we're going to do is we're going to call this hydrogen phosphate ion. Now notice that it is still charged. So it is still an ion. It's not a compound, it's an ion, because it still does have a charge on it. Anything that has a charge is called an ion, period. Okay, now we can actually, what about if we add another hydrogen? Now we have 2 hydrogens and a phosphate, still charged, but now we have 2 hydrogens. It has to be different. There's a difference between these two. So this one is called dihydrogen phosphate. Pen's not working very good. Ion. What about if we add another one? Notice that there's no charge on it. It's no longer an ion. So we're not considering that right now. That's not an ion anymore. So we're going to talk about that in a few minutes, but it's no longer an ion. Okay, in your exercise, so they want to know what is hydrogen sulfide ion. So we know that hydrogen sulfide, so we know that we're involving H plus. Sulfide ion is sulfur. It's in group 6. That means it has a -2 charge. Combine those together, and we'll end up with HS minus. Like so. Okay. Now, what about if for this compound here? Now, anything that starts with hydrogen that has a charge is going to be one of these hydrogen ions. Okay. If it starts with hydrogen, it doesn't have a charge, then it's an acid. And we'll talk about those in a few minutes. But this one has a charge and it starts with hydrogen. So that means that essentially what we got is we got H plus and SO3 2 minus. Let me break it apart. Okay, so that's going to be a hydrogen ion, and this is SO3 2 minus is sulfite. Sulfite ion. So this would be called hydrogen sulfite ion. So, okay. All right. Now, so we covered ions. Now we're going to talk about compounds. There's three types of compounds. There's ionic compounds, covalent compounds, and acids. For our purposes in the lab, anything that starts with hydrogen is an acid. Anything that's compound that starts with a metal is an ionic compound. And anything else is covalent. So essentially something that starts with a covalent compound will be covalent. Okay. So the easiest way to recognize these is to first look at the first element, either in the formula or in the name. If it's a metal, it's ionic. If it's a non-metal, if it's hydrogen, then it's an acid. If it's a non-metal, then it's covalent. Okay. So being able to identify these is really important for being able to name them. You're expected to be able to go from name to formula or formula to name either way, back and forth either way. Okay. So the first compounds are the easiest ones. These would be ionic compounds. Now remember, the one trick for this is that ammonium is considered to be a metal. So NH4 plus is considered to be a metal. So that means anything with it would be an ionic compound. Okay. So now ionic compounds, unlike polyatomic ions, have no charge on them. So that means that the positive charge for the metal and the negative charge for the non-metal have to add up to be 0. So for instance, if we have calcium ion, which is a metal, and we have chloride ion, which is a non-metal, to add these two together, we want them to be able to add up to be 0. So that means that obviously, hopefully from seeing this, you probably see that we need 2 chlorines to balance out 1 calcium, right? Like so. Now the number of atoms in an element, we'll use a subscript for to represent that there's 2 chlorines in this. Okay. This right here is calcium ion, and this is chloride ion. And so this compound would be calcium chloride. So, okay. Notice that calcium is a group 2 metal, which means that we don't need a Roman numeral for it. We know that it's got to be a +2, and so forth. Okay. Now, if we, so that's going from, okay, now, let's see. Okay, likewise, if we, this one is iron 3 ion, and this is oxide ion. And so we need these to add up to be 0, obviously odd and even number. So 2 of these and 3 of these. Also notice that there is no ion in the name. This is a neutral compound, so they add it to be 0, which means that there is no ion at the end of the name because it is a neutral compound at this point. Okay, now that's taking the ions and creating the name, basically from the formula. So yeah, so here we go. Actually, the exercises will be good practice for us for this. Okay, so now what you're most responsible for is being able to go from name to formula or formula to name. So remember that with these, that if you're going from name to formula, the formula has to add up to be 0. Okay, so the first one in exercise 4 is strontium bromide. Now, hopefully by the time you are responsible for this, you quickly recognize that this is a metal, which means this is an ionic compound. So strontium is Sr, and since it's in group 2, then it have a +2 charge on it. Bromide is a nonmetal, there's the IDE on the end of it, and it's in group 7, so that means it has a -1 charge to it. So when you combine these, then we're going to end up with now along these lines, let's see, we don't really have one in here, but one thing I want to show you is that in a lot of, and I've seen it in college level non-majors, general introductory chemistry textbooks. So I know it's in high school textbooks, but so for some of you, hopefully you can look at this and you can go, oh, this one has a +2, this one has a -1. So we need 2 of these to be able to balance it out, right? That's the way we want you to do it. That's the way you should be doing it. The problem we run into is using what they call the crisscross method. And let me show you real quick. You don't need to necessarily write this down. If you're used to doing the crisscross method, let me show you what your mistake is. You do this, if you don't do the crisscross method, ignore this. Don't learn it this way. It's a bad thing. It causes lots of problems. But if you're using this crisscross method thing, like this, if anybody recognizes this, what you end up with is this. What most of the time they don't teach you, or you forgot, one of the two, is that there's one more step for the crisscross method, which is reduced to the lowest common denominator, which means that this would be reduced to MgO. This is correct, this is incorrect. So if you're using that silly little crisscross method, first of all, it's going to mess you up. Second of all, if you do it, you've got to do that last step. So magnesium oxide is MgO. It's not Mg2O2. So if you're doing the crisscross thing, you have to remember the last step, which is to reduce to the lowest common denominator. But it'll mess you up more times than it'll help you. The best way to do it is to really take a look at your charges, 2 plus here, -1 there. Same thing with this one. If we look at the original thing that I had, okay, magnesium got a +2. Oxygen got a 2-. How many of each do I need? Oh, I need 1 of each. Boom, I'm done. I know it's MgO. So what's the point in doing the little crisscross thing? The crisscross thing just messes you up, basically. So it slows you down. I'm not sure why they teach it. I think it's some sort of shortcut or something, but it doesn't work that well. It works okay for some things, but a lot of things it doesn't. Magnesium oxide, it does not work for. Most of the time, most students will write this as Mg2O2 because they're using that crisscross thing. So again, it's a mistake. That is wrong. Mg2O2 is not magnesium oxide. MgO is magnesium oxide. Same thing when I've seen lead-4 oxide. It's PbO2, and a lot of times students will write it as Pb2O4. And there's a whole variety of other ones, calcium oxide and so forth like that. So the little crisscross thing will mess you up unless you're doing it correctly. So if you've been taught it correctly, I don't think it's really useful, but if you've been taught correctly, then that's fine. But just realize if you do insist on using it, you do need to do that, the last thing of reducing to the lowest common denominators on those. So just be aware of that, okay? Is the main thing. But I'd highly discourage you from doing it. I would just look at the two charges on your two ions and balance it from there. The crisscross thing is not really that useful. It's kind of helpful for like iron 3 oxide or something like that, but not enough to justify all the mistakes it's going to cause you. So it causes a lot more problems than it actually solves. Okay, let's go on to the next example. Okay, next one is cobalt 2 nitrate. So now, cobalt 2 nitrate does not mean there's two cobalts and one nitrate. What it means is cobalt 2 refers to, it's a cobalt 2 ion that forms the compound. And then nitrate. You're responsible for knowing that nitrate is NO3 minus. And then we take a look and we say, okay, there's 2 plus on this one, there's a -1 on this one. So that means we need 2 of these, right? So we write that as like this, like so, okay? Note that the nitrate does need to be in parentheses, otherwise it would be NO32. And so it does need to be in parentheses, and then we put a 2 to represent the number of nitrates that we have in there, okay? Again, the 2 up here refers to the charge on the cobalt. It does not refer to the number of cobalt atoms. All the time we'll get CO2 NO3. That's incorrect, that's wrong. So the Roman numeral 2 refers to the charges on that ion. Okay, sodium acetate. The sodium is a +1, the acetate's a -1, so we're not going to bother with that one. Let's go on to the formulas to names. So again, you'll see this all on that handout that I've got posted on there. So we have, we want to know what the name of this one is. And so when we look and we go, oh, that's a metal. That's a non-metal. This must be an ionic compound. This is, you know, essentially 3 calcium 2 pluses. So always double check your charges here just to make sure that they make sense. So nitrogen is a 3 minus because it's group 5, and there's 2 of those. And so -6 here, +6 there. So it looks like everything's balanced out. Calcium is a group 2A metal. And so it does not need a Roman numeral. So this would be calcium nitride. So again, for the non-metals, if it's a pure element, it's IDE. So this is calcium nitride. And then now we get to the tricky one, which is a good one. Fe2SO4 3. Okay, this is where things get challenging. All right, so we know this one is iron, right? And it's a metal, so that means it's an ionic compound. And this is sulfate ion. Now the problem is that iron needs parentheses. So we got to figure out what the charge is. We can't tell just by looking. It's not 2. I know it's Fe2SO43, but that doesn't mean that this is a 2. That's not a Roman numeral 2. That just refers to the number of atoms that are in there. So we need to know what the charge is on that, what the positive charge is on the iron. So what we're going to do is we're going to use a little trick. So 2 times whatever Fe is plus 3 times, we'll go ahead and put it as sulfate right now, has to equal 0. They have to add it to be 0. So we know that the sulfate is -2. So that means 2 times Fe plus -6 has to equal 0. And so 2Fe has to equal +6. So that means that Fe has to equal +3. And that's what goes up here. Okay, so with an ionic compound, the positive charges and the negative charges have to add up to be 0. Otherwise, it's not an ionic compound. So that's the way we would determine that one. Okay, the last one they're just trying to be kind of a little tricky with. Nothing really special. It's not really that unusual, but you look at this one and you go, oh, nitrogen, hydrogen, carbon, nitrogen. Oh my God, what's going on? I can't recognize anything. Relax. Just look for something you recognize. Hopefully one of those two you would recognize. Maybe this one or that one. It's just two compounds. So this is ammonium, which is NH4 plus, and cyanide ion, which is CN minus. So this one would just be ammonium cyanide is all. They're just throwing it in there so that you kind of get a little confused by seeing all the different elements that are in there. Okay, all right. Okay, next is covalent compounds. So if it doesn't start with a metal and it doesn't start with hydrogen, then it's covalent. It should start with a non-metal besides hydrogen, and in which case it would be covalent. You're going to study covalence in lecture in module 7, starting with module 7. For now, all we want you to do is nomenclature. That's it. So you just have to be able to name them, go from name to formula or formula to name. Either way, that's all. So you don't have to understand it or anything like that. In fact, what you'll recognize from this is, say one of the easiest ones, CO2, is that if you try to do this by the rules of ionic compounds, this one's a -4, this one's a -4. It doesn't have to be 0. It doesn't work, right? The nonmetals are all negatives, so you can't do it that way. So again, all you need to do is just be able to do the names, that's all. So this one, hopefully all of you recognize as carbon dioxide. Okay. This one, now, the mono is not necessary. What it is really to be able to quickly indicate that it's a covalent compound. If you said carbon oxide, then it may be a little not apparent to somebody that it's a covalent compound. By putting the mono in there, then that you really kind of emphasizes the fact that, hey, this is a covalent compound, and you immediately recognize that it is. Because what you're doing is, in a name for a covalent compound, you're looking for a prefix. When you see the di in carbon dioxide, immediately di, oh, okay, covalent. Tri, tetra, anything like that. The prefix really tips you off immediately in the name that this is a covalent compound. So the mono is typically used to kind of emphasize that. So, so the mono in carbon monoxide is really just to give it a prefix so that you can immediately recognize it. And it's just, it's not necessary. It's just kind of done by convention. And so if you ever saw carbon oxide, it might take you a minute to go, okay, well, let's see, those are both nonmetals. That must be blah, blah, whatever like this. It would take you a little bit longer, whereas the mono makes it a little bit faster and a little bit easier and a little bit more obvious. So that's the reason why IUPAC, the International Union of Pure and Applied Chemists, tend to like having that in there, is just so that it makes it really immediately apparent that this is a covalent compound. If it's not in there, it's a little bit more ambiguous. It just takes you a little bit longer to recognize it, is all, but it's perfectly valid. Sometimes you'll see like nitrogen oxide or something like that, and it's just, again, the mono typically is there for convenience, just to make it really clear, quick, and easy for the reader to immediately recognize that as a covalent compound, but it's by no means necessary. Okay, you should definitely know the first, let's say, 5 of the Greek prefixes. So mono, di, tri, tetra, penta, and then it's helpful if you know the rest of them too: the hexa, hepta, octa, nona, and deca. Things like nitrogen tetrafluoride, your example that you're given in here, is pretty common, and so forth like that. Okay, now there are 3 covalent compounds that are strictly called by their common names. Hopefully you recognize H2O is water. Water is not referred to as dihydrogen monoxide. Sorry. If you want to have a little fun, sometimes you got a little time to kill or something like that, do a little internet search for dihydrogen monoxide. You can find all kinds of little funny urban tales and stories and stuff like that about tricking people with dihydrogen monoxide and how dangerous it is. But nonetheless, for our purposes in our class, H2O is called water. It's not called dihydrogen monoxide. Dihydrogen monoxide is incorrect, is wrong. Okay? H2O is called water in this class by convention. Okay? The other one is, these three should be recognized on sight by their common names. This is called ammonia. Notice it ends in an A, not an IUM. So ammonia is a neutral covalent compound, nitrogen with 3 hydrogens. It's not called nitrogen trihydride. It's called ammonia. You should recognize it as that. Also in the little handout help sheet that I've given you, provided to you, it also indicates these, is that you should look for these. So this one again is not dihydrogen dioxide. This is called hydrogen peroxide. That's primarily because this is the peroxide ion, and that's just the way we name it. So in a way, this could be kind of classified as an acid, but we list it as a covalent compound, and its common name is hydrogen peroxide. So you should recognize it as that. Notice this is a covalent compound, not an acid. So it's one of those ones that's kind of the exception to the rule, and that's listed on the handout also. So these three go by their common names. So you should be aware of that. Everything else, if it starts with a non-metal, then it'll follow the covalent naming rules. So going from name to formula or formula to name, either one. Okay. In exercise 5, carbon dioxide. So again, the di should be a tip off that we're talking about a covalent compound. So in the handout, that's what I've told you is look in there. I mean, one of the things, if you're given a name, look, do you see a prefix? If you see a prefix in there, it's covalent. Boom. All you have to do is just write out the number of atoms that they tell you to. So carbon dioxide, the di tells us it's covalent. So we're like, oh, there's a prefix. Okay, that means it's covalent. And then carbon dioxide. So that means there's 1 carbon, 2 oxygens. So this is CO2. Now, dinitrogen oxide. Notice that this is not dinitrogen monoxide because there's already a di in the nitrogen. So it's not necessary. We've already got a prefix in there. We already know that it's a covalent compound. There's no need to put mono on there. So again, would it be incorrect? I don't know, but it's not necessary. So typically we go for brevity in science. So dinitrogen oxide, 2 nitrogens, 1 oxygen, so N2O. And then SiO2. So first thing we notice is silicon is a non-metal. And so this must be a covalent compound. And so all we need to do is just use prefixes. There's 1 silicon, 2 oxygens. We don't need a mono on the silicon because the oxygen's already got a prefix on it. So this would be silicon dioxide, much like the carbon dioxide above it, or next to it. And then PBr3 is a phosphorus and 3 bromides. So it'd be phosphorus tribromide. Now, notice that both compounds in an ionic compound are both, like for the formula to name, both are nonmetals, but only the second one is given the IDE prefix. So it's silicon dioxide, carbon dioxide. Notice it's not carbide, carbon dioxide. So the second one, however it's written, the second one is the one that gets changed to IDE. The first one shares its common name, its regular name, its standard name. So phosphorus tribromide. Okay, now with the acids, that's the last class. Anything that starts with hydrogen in this class is considered to be an acid. Now, under certain circumstances, you can read in module 0 of lecture is you can have hydrogen compounds, for instance, hydrogen chloride or something like that. But for our purposes, everything is aqueous. And so anytime any of the hydrogen compounds in this class in lab are going to be considered to be acids. So if your formula starts with hydrogen, that means it's an acid, unless it's water or hydrogen peroxide. And so anyway, so there's two types of acids. There's binary acids and there's polyatomic ions acids. So the first one is the easier one is the binary acids. So binary means that it's hydrogen and one other compound. So again, hydrogen forms a +1 charge, just like we saw with the hydrogen-containing ions. And so if we combine it with a negative charge, with a nonmetal, so this is only combined with nonmetals, then we would need one of each to balance that out. Again, what we're making is a neutral compound. So one hydrogen and one chloride combined together to make 0. So in other words, a neutral compound. Okay. So for binary acid, we're going to use hydro. The chlor is going to refer to what the other element was, and then ic acid. So hydrochloric acid, hydrofluoric acid, hydroiodic acid, hydrosulfuric acid, anything like that. Hydroselenic acid, so any of those. Now, what about hydrosulfuric acid? So now what about if we combine H plus with sulfide ion? Like so. Well, now this is +1, this is 2 minus. So that means that we need 2 of these. So this is going to give us H2S. This one would be, again, hydro, because it's binary. Hydrosulfuric acid, like so. Okay. All right. So in exercise 5 for the binary acids, first they give you the name. And for names, if you see acid in the name, that means the first element is hydrogen. There's hydrogen with something else. So, and if you see the hydro, it means it's hydrogen and one other thing. So hydroselenic means that what we're doing is we're combining H plus and selenide, which is going to be group 6. That means it's 2+ charge. I mean 2 minus charge. Sorry, minus, not plus. And so we need 2 hydrogens and 1 selenide. So this is going to be hydroselenic acid. Hydrofluoric acid will be just like the hydrochloric. So it's H plus and F minus. And then what is HI called? So for HI, we look and we say, oh, it starts with H, that means it's an acid. So we know it's an acid. And then we want to look and say, does it have only one other element, or does it have oxygen in it? Or is it polyatomic, basically? But does it have oxygen in it? No. So that means that we need to use hydro in the name. So that one would be hydroiodic acid. And then the last one on the H2TE is tellurium plus hydrogen. There's no oxygens in there. So that means it's going to be hydrotelluric acid. Okay. We'll kind of combine these together on the last exercise as soon as we finish this up right here. Okay. Now, we can also form acids with polyatomic ions. These are called oxyacids because almost all of the polyatomic ions have oxygen in them. So these would be polyatomic, the oxyacids. Okay, now they give you basically 2 rules. Yeah, there's only 2 rules for this, for the names. Is if your ion ends in 8, you're going to change it to ic in the name. And if your ion ends in ite, you're going to change it to us, O-U-S. And that's it. That's all. So relatively easy. So we know that chlorate ion is ClO3 minus. So if we add H plus to that, then now we have an acid. This one would be, chloric. So 8 changes to ic, acid. So 8 becomes ic. And then the other rule is for the us's, for the ites. So chlorite ion is ClO2 minus. If we add hydrogen to that, form an acid, HClO2, and this is going to be chlorous acid. Okay, so again, all we did was change the suffixes all. Chlorite ion becomes chlorous acid. Chlorate ion becomes chloric acid. All right, now the prefixes would stay the same. So if we started with ClO4 minus, that would be HClO4. And so this would be, the per would still stay the same, and the ic would still stay the same. So this would be perchloric acid. And then we can also have the hypo down here. That would be hypochlorous. I think hypochlorous is bleach. So you can check on a bleach bottle if you're home. So the only changes with the oxyacids is you take the name of the ion and you change ate to ic or ite to us, and that's it. So it works the same way. So carbonate ion would form carbonic acid. Nitrate would form nitric acid. Nitrite ion would form nitrous acid. Sulfate would form sulfuric acid, and sulfite ion would form sulfurous acid. Sulfurous acid is usually what's used for most bathroom cleaners. So if you check on a bathroom cleaner spray bottle, then you'll see that it's sulfurous acid typically. Okay, now so let's go ahead and talk about exercise 6 real quick, and then we'll move to the very last part, and we'll finish that up real quick. So phosphoric acid. So again, this is going from name to formula. And so first of all, we know it's an acid. So that means it has hydrogen. We know that. There's no hydro, which means it's oxy. And then it ends in ic, which ic is referred to 8. So that means that this is phosphate. Ion. And so, which is PO4 3 minus. And so phosphoric acid would be hydrogen combined with phosphate ion. Okay, periodic acid sounds kind of a little unusual, but this is one you should know. Okay, so first acid tells you that there's hydrogens there, and then we got this part. The ic comes from the 8, and so this is, the ion is periodate, which is IO4 minus, and so this would just be HiO4. Okay, bromous acid, again, the OUS will come from the ITE. So this comes from bromite ion, and that would be BrO2 minus, and so it'd be HBrO2. Okay. Now, for the formulas to names, so HBrO, like so. Okay, again, this is an acid in this class. So this is not hydrogen hydrobromate. We're going to call this by its acid name. So keep that in mind. So this one is hypobromite ion, which means that we're going to change the ite to us. We're going to add acid. So this one's going to be hypobromous acid. H2SO4 is sulfate ion, and so that'll be sulfuric acid. And HNO2, it comes from nitrite ion, so that'll be nitrous acid. Okay, now, again, I've got a handout posted on here for you, but we'll just kind of wing it a little bit for this one. You'll have it when you I've actually got it right here. So you'll have it when you go to work on your exercises for homework. So the very last one, this is essentially what you're going to be doing in your homework. So the last exercise on page 12, this is really the one that shows you kind of what you're expected to do and what you'll be doing on your homework and stuff like that. So you're just going to start with a formula. First thing you need to do is identify what type of compound. Is it ionic, covalent, or acid? And then what type is it within that? So if it's ionic, is it a main group or is it transition? If it's acid, is it oxyacid or binary acid and so forth like that? Okay, so on the flow chart that I've given you, basically what I said, if you're given a formula, which is what we're starting with formula. So take a look at the formula. Does it start with hydrogen? If it does, it's an acid. If it starts with a metal, then it's ionic. So the exception to the acid would be if it's water or hydrogen peroxide. But look for hydrogen, look for a metal. And if not, then it's covalent. So take a look at the first one we have here is K2S. I'm going to put it up here. So K2S, what we do is say, oh, does it start with hydrogen? No. Does it start with a metal? Yeah, potassium is metal. So it starts with a metal. And so the two metals would be, the metal would be potassium. And then the non-metal is sulfide. And then the next thing we need to do is we need to look and we need to say, does potassium need a Roman numeral? So potassium is in group 1A, which means that it does not need a Roman numeral. So the compound would just be potassium sulfide, like so, and we're done. Okay. Second one we have is P2O5. So we're looking to say first, does it start with hydrogen? No. Does it start with a metal? No, wait, phosphorus is not a metal. That means it must be covalent. So it's covalent. So for covalence, all we do is we use prefixes. So, and the second one ends in IDE, the first one doesn't. So we would say diphosphorus pentoxide. And that would be a covalent compound. Okay. Third one is FeC2H3O23. So for that one, we would look and we would say, oh, it's iron and it's acetate. And does iron need a Roman numeral? Yes, it does, because it's not group 1, group 2, or aluminum. And so we'd say, okay, acetate's -1. There's 3 of them, so it must be 3. So this would be iron 3 acetate. All right, the acids are usually the ones that give students the most trouble in here. So again, hydro means there's no oxygen. No hydro means there is oxygen. So HBr, we'd say, does it start with hydrogen? Yes. Okay, that means it's an acid. Okay, HBr is an acid. And then the main thing with that one is to look and say, is there oxygens? There's no oxygens. So that means we do not, or that means we do use hydro. So 4 would be hydrobromic acid. The hydro one's always in an IC, never in us, but so hydrobromic acid would be the name for that one. It is an acid. Okay. The last one, number 5, the last formula is HNO3. So we look at that one and we say, does it start with hydrogen? Yes. So it's an acid. Does it have oxygen in it? Yes, it does have oxygen in it. So it has oxygen, which means that we're not going to use hydro. And we just need to know what the name of this polyatomic ion is, this oxy ion is. And so this one is nitrate. Nitrate ion. So that means that we're going to change 8 to ic. And ion to acid. So this one would be nitric acid. All right, now name the formula. So rubidium oxide. First thing we look and say, does it start with hydrogen? From the other sheet. So look and say, do you see acid or do you see a prefix? Is the main thing you're looking for, or a Roman numeral? So for this rubidium oxide, we say there's no acid, there's no prefixes, and there's no Roman numerals. So it must be just a main group ionic compound. So rubidium oxide, rubidium, when we look on there, is in a group 1, and oxide is in group 6, so it's 2 minus. So this one would be Rb2O, like so. Next one, nitrogen triiodide. Do you see acid? No. Do you see a prefix? Oh, I see a prefix, tri. So that means this must be a covalent compound. So covalent compound, and there's 1 nitrogen and 3 iodides. So Ni3. Hydrogen peroxide. This is one of the 3 common covalents you should recognize on site. So hydrogen peroxide is a covalent compound, and it's H2O2. So it is covalent. Okay, hypobromous acid. So for that one, you see acid is in the name, so it's easy to spot. So hypobromous acid. And you look and you say, basically what we're looking for is, does it have hydro in there? No, it doesn't. It has hypo, but it doesn't have hydro. So that means that it must be an oxyacid. Again, what we're looking at is this part right here, and us would be ite. So hypobromite ion, which would be BrO minus, like so. And then we want to combine those with H pluses. There's 1 plus, 1 minus, so just HBrO. You are expected to be able to do all this pretty easily. Okay, cobalt-3 phosphate. So again, the 2 refers to the charge on the cobalt, Roman numeral 2, and then phosphate. Whoops. I don't even know what phosphate is anymore. Okay. And then when we look at these, +3, -2, common, it's going to be 6. So that means we need 3 of these, and we need 2 of these. Like so. Like so.
Your nomenclature discussion is now complete. Here is a quick summary for your review. Make sure you complete pages 7 to 12 in your lab manual based on your professor's instructions.